Hello, everyone. In this talk, I'll be presenting Checkmate, zero performance overhead model checkpointing via network gradient replication. Machine learning is the latest, fastest growing workload around today. This report from Applic.ai illustrates this trend. We have seen a similar version of this in the morning keynote talk, where the required amount of compute for training frontier models grows by over 6 times every year. To support such growing demand, operators scale out their compute resource by connecting a massive amount of GPUs inside data centers. Zooming into the recent years, Meta's Llama 3 405B model was trained on a cluster of 24,000 H100 GPUs. And less than a year later, the Llama 4 Behemoth model was trained on a cluster 4 times this size. And such a demand scale brings failure as a major challenge. In the Llama 3 training report, for instance, Meta has reported a detailed failure analysis and reported 419 failures over the 54 days of training that required a recovery, which wastes about 2 million precious GPU hours. To minimize this wastage, a fundamental operation existing system rely on is DNN checkpointing. To prevent failures from wiping out progress, training systems periodically save the training states, including the latest copy of the model parameter and optimizer states, to a reliable media as a checkpoint. Upon a failure, these systems restore the checkpoint state and restart the training. This checkpointing and restoration allows training systems to make progress even in presence of frequent failures. Let's look at how a checkpoint is produced during training, starting with how DNN models are updated. DNN training is an iterative process where an iteration begins with a batch of input samples being processed by the model with a given state at iteration t here. During the forward pass, the samples propagate through the model to compute the loss. And the backward pass then subsequently consumes the loss and produces gradients of this iteration t. And then the update step applies this gradient via an optimizer, such as SGD, Atom, or Atom W, using the model state at iteration t+1. This forward, backward, and update cycle constitute one training iteration and generate a new version of the model. And suppose we wish to obtain a checkpoint following this update. The traditional checkpointing mechanism uses a copy-persist abstraction, which is typically divided into 2 steps. The first step is to make a copy of the training state. Then the checkpointing system sends this checkpoint to a reliable medium, usually other storage node attached to the network. This is the persist step. The reliable media can be persistent storage or replicated volatile memory. In the most straightforward implementation of this, the GPUs pause to finish the copy-persist checkpointing, and then resumes training. This is the synchronous checkpointing approach. Here, both copying training state out of GPU as well as persisting it to remote storage cause GPU to sit idle and wasting GPU resource. To reduce such overhead, more sophisticated implementation introduces asynchronous checkpointing, where the copy step overlaps with the next iteration of computation. However, the copy step here causes contention on GPU memory bandwidth. And furthermore, such approach still requires the GPU to finish copying before the next optimizer step, and then wasting GPU resources, especially when checkpointing frequently. And because of all of these overheads, checkpointing is done infrequently. But that is not ideal either. For example, in this diagram, checkpointing occurs after every 40 iterations. Now, if the training fails at iteration 70, upon recovery, the system will have to repeat iteration 40 to 70 before making any new progress. And as a result of this, we are left with a trade-off, either checkpointing often but suffering GPU overhead, or checkpointing seldomly but risking more repeated work. And this is a trade-off people aim to break. Here's a quote from the Llama 3 paper regarding a future task, where their aim is to minimize GPU pause during checkpointing while increasing checkpointing frequency. Checkmate, our system, breaks this trade-off by providing a new approach leveraging the network to enable frequent and low overhead checkpointing. Our goal here is to achieve the theoretical best case, which is to check a checkpoint per iteration with 0 GPU overhead. And this is what our system Checkmate actually provides. Let me show you how we do it. The traditional approach requires the GPU to produce new checkpoints and introducing unavoidable overhead. Conversely, if we can remove the GPU from the checkpointing path, the overhead disappears entirely. We show this is achievable through an alternative formulation of the per iteration checkpointing process. The slide here shows, again, the model update step, where we apply gradient via an optimizer such as AtomW. A checkpoint is an entire copy of the model state at iteration t. And our key idea is that a checkpoint here can be advanced by executing this same update step. Given the gradient, applying the identical updating rule to this checkpoint will yield a new checkpoint that matches our model state at iteration t+1. And because this checkpoint resides off GPU, this update is transparent to the GPUs and will not have any overhead. Then the problem is just how do we get these gradients to our checkpoints? Well, in any hybrid parallel training with replication, the gradients are synchronized in the network across replicas of the model across every GPU, every iteration. This means the network sees all of these gradients naturally. And hence, we can leverage the network to replicate the gradients to these nodes that stores the checkpoint and repeat the update step. This is our key idea in our system, Checkmate, performing checkpointing on storage node through network gradient replication and achieve per iteration checkpointing without any performance overhead. Checkmate uses 3 components. At the top here are the training nodes running unmodified DNN training code. These training processes use Nickel, NVIDIA's communication library for gradient synchronization. And we only need to implement a Nickel plugin at the training side in Checkmate to assist replication of the gradient with tagging. And as a result, the checkpointing process remains transparent to the training process. During normal training, GPUs exchange gradients to keep the models in synchronization. Here in the network, instead of just forwarding gradient between the training node, switches replicate them to the storage node with multicasting. Our implementation here utilizes a P4 programmable switch, but any switch supporting multicasting will suffice. And lastly, on the storage end, the storage node uses these gradients to maintain the shadow model and optimizer state on the storage cluster. This serves as the checkpoint, allowing us to recover from any training node failure without progress loss. More precisely, instead of the traditional copy persist abstraction like shown above here on the slide, Checkmate uses a multicast update abstraction for checkpointing. In Checkmate, both the training nodes and the storage node participate in the checkpointing process. During normal iteration of the training shown here, the network multicasts the gradient to both the training cluster for regular synchronization and the storage node for updating checkpointing. Upon receiving these gradients, the checkpoint node updates the local snapshot incrementally, while the training server proceeds with its iteration normally. This process continues for every iteration to provide per iteration checkpoints. While this process sounds straightforward, to realize Checkmate, we need to solve a few challenges. The first one is network load management. To replicate gradient, Checkmate requires enough bandwidth or links to be added across the storage and the network to support replication. However, during gradient synchronization, every GPU in the training cluster sends its traffic at line rate. The naive solution of replicating all of these traffic requires us to provision the same amount of bandwidth to storage as to training, which is way too much resource overhead. Fortunately, there's a lot of redundant information during gradient transmission, and by leveraging these redundancies, we designed a replication algorithm that selectively replicates these gradients, and as a result, only need twice the per GPU bandwidth for each group of GPUs participating in the same collective communication group, regardless of the group size. Let me show you how this is done by giving an example of how Checkmate selectively replicates gradient during the synchronization process with the ring or reduce algorithm. More precisely, I will be showing the altogether steps at the end of the or reduce algorithm. Suppose we have 4 pieces of gradients and we want to synchronize them across 4 GPUs. Here, we start with everyone holding 1 piece of this synchronized gradient, and at the end, we need to have every GPU to carry every piece of gradient. And in addition, we want our checkpointing storage to also have all of these gradients. The ring or reduce algorithm has each GPU to send gradients to their neighbors for a few rounds. So here, let's begin the round 1 of transmission. Here, instead of replicating everything, Checkmate only replicates 1 of them, since this algorithm will not be finished after this round, and we have plenty of chance for the other gradients to be replicated. In this example, I'll replicate the gradient transmitted on the bottom link, so the green one. At the end of round 1, the cluster state is this. Then round 2 of transmission begins, where we transmit another gradient, and we perform the same replication on the bottom link to the storage cluster and get the blue gradient into the gradient storage. Then run 3 begins, and we do the same replication. But now, there is a problem. This is the last round of this algorithm, and we need to have all of the gradients on the storage node afterward. And hence, this is where we need a second replication stream from another link for this transmission to fill the red gradient and finish our algorithm. What we see is that we need to have replicate one piece of gradient information every round of the transmission, except the last one where we need 2 of them. Hence, for each collective communication group of any size, we only need twice the per GPU bandwidth to mirror the entire set of the gradients. Now, we have optimized for gradient multicasting across iterations to reduce the network load. The next challenge is ensuring that gradients are reliably delivered to the storage nodes. Checkmates rely on gradient multicasting, but if packets carrying these gradients are dropped, the storage node can receive incomplete gradient updates, which leads to corruption or incomplete shadow models, affecting recovery and model consistency. Now, to ensure that the gradients are reliably delivered to the storage node, Checkmate implements lossless gradient multicasting or forwarding, which leverages PFCs, or priority-based flow control, which creates a lossless network across the storage and the network, just like today's training network. The solution is enabled by the fact that all multicasting downstreams can backpressure the upstream to ensure losslessness. In our implementation, we tune the switch and NICs buffer management to ensure optimal performance and losslessness at the same times. And for the storage to verify we have indeed received the full set of gradients, we implement a handshake mechanism between the switch and the storage and uses sequence numbers to track data integrity. Forward error correction code, or FECs, are further leveraged to ensure packet corruption doesn't happen. Now, these solve the training and network side of the challenges, but one more challenge remains on the storage end. Although the optimizer step is computationally cheap compared to these forward and backward paths, the storage node only have CPUs to execute it. But there is a tight deadline. This update step needs to complete before the next set of gradients are fully received. Otherwise, there will be a backlog. But what if the storage CPU is weaker, or the DN model just have larger parameter count and require more computation time? Fortunately, the optimizer step, along with the checkpoint themselves, can easily be sharded. Most optimizers in practice, like Atom and AtomW, are functional and independent. That is to say, in these optimizers, an update step happens independently and deterministically on each parameter, allowing them to be partitioned efficiently. Checkmate leverages this property and partitions the checkpoint, scaling out the optimizer step across multiple storage nodes. By parallelizing the optimizer computations, Checkmate ensures a shadow model remains in synchronization with the training node without any stalling of the update. The result of Checkmate is the best robustness at the ideal throughput. We have implemented Checkmate end-to-end and trained multiple models to evaluate Checkmate's performance. In this presentation, I will show the result of training a Llama 2 13B model on our 12 A100 GPU nodes with 100 gigabits per second of link with 4 storage nodes in CPU servers for the updating. On this plot, the y-axis is throughput in tokens per second. Higher is better. And the x-axis is the number of checkpoints completed in 1,000 iterations. More checkpoints here means more robustness, and we want to be on the top right corner of this graph. Let's start with some baselines. The brown dot is our no checkpointing baseline, which is the optimal performance case that gives you the maximum throughput. But any failure here means restarting the entire training over. Next is PyTorch's highly optimized asynchronous checkpointing implementation, shown with the red dot, which results in about a 4 times slowdown in training throughput when checkpointing every iteration here, despite being highly optimized. Next, we look at the recent proposal, CheckFreak from Fast21. This is a system aiming to adaptively tune the checkpointing frequency and minimize the checkpoint overhead. It matches the baseline throughput, but checkpoint infrequently, so you would still lose a significant work upon the failure. Lastly, let's look at Checkmate. The blue dot here is Checkmate, having a training throughput within 0.8% of the baseline throughput, while checkpointing every iteration, achieving high performance and efficient recovery at the same time. Compared to the state-of-the-art approaches, Checkmate generates up to 34 times more checkpoint, or increases the training throughput by up to 4.3 times at identical checkpointing frequency. Finally, we evaluate how Checkmate's performance scales with the number of storage nodes involved. We show here a micro benchmark of how optimizer step time scales with the number of CPU servers or CPU cores we use, where the x-axis here shows the number of CPU cores used, and y-axis is the step time in milliseconds. Here we use up to 4 28-core machines, so up to 112 cores total. And, here we show the result of 2 variants of the GPT-3 model with 1.3 billion and 6.7 billion parameters. The optimizer step here goes down when utilizing more cores for the computation. And such computation is easily distributed among multiple machines. The vertical dashed line here represents machine boundaries as we scale above a single machine. And for this example, even a single 28-core server keeps up with training a 6.7 billion parameter model with a reasonable batch size, local batch size of 5 here. And 3 of these storage nodes will be able to support the worst case local batch size of 1 for training the 6.7 billion parameter model. That concludes this talk. In summary, we have developed Checkmate that provides zero GPU overhead checkpointing with network assistant by using the new multicast update abstraction to replicate gradient in the network and repeat the update step on the storage node. Compared to existing systems, Checkmate provides 5 to 34.5 times more frequent checkpointing or achieve 1.3 to 6.5 times throughput at identical per iteration checkpointing frequency. The code base of Checkmate is public on the GitHub link here, shown here on the slide. Thank you for listening and happy to answer any questions.